Today we will start with differential forms, and this is really to rediscover integration. Whenever you've integrated before, you've really integrated differential forms. If you've done a p-dimensional integral, you've really integrated a p-dimensional differential form. So we start with differential forms, and then towards the end of the course, not the end of the course, towards the end of the lecture today, I'll take you on a mathematical rocket ship, and then we go up to the mathematical stratosphere and have a view over the mathematical landscape. It's just an excursion, but it should be fun. Okay, so differential forms. They're also called exterior differential forms, or also just called forms. As I already mentioned, p-dimensional integration is always integration over a p-form, over a differential p-form, or exterior p-form. We need some preparation for this. Consider the cotangent space to a point P. So we choose a point P of the manifold, and we consider the cotangent space, Tpm star. Every element of the cotangent space, every cotangent vector, is a linear map. It's a linear map that maps tangent vectors into real numbers. So omega, a cotangent vector, is mapping a tangent vector into a real number, omega of psi. The end of the last lecture, we saw that an ecotangent vector can also be viewed as a covariant tensor of rank 0, 1. The cotangent space is just a tensor space. It's the space of tensors of rank 0, 1. Now let's consider more general covariant tensors. Let's consider tensors of rank 0R. Now these things are hungry for R tangent vectors. So Tpm of R, the space of tensors of rank 0R, is the tensor product of R copies of the tangent space at the point P. It's a much higher dimensional space because the dimensions multiply, of course. Each element of the space of 0R tensors, every such nu, is a multilinear map. You can feed it R tangent vectors, or you can feed it any tensor entry, any contravariant tensor of rank R0, and you get out a number. And it's going to be linear in each one of those arguments, in each one of those factors. So in particular, if we take R tangent vectors, psi1 to psi r, each one of them being an element of the tangent vector space, then an element of this space of 0R tensors, such a nu, a 0R tensor, is going to map those R tangent vectors in a linear fashion into a real number. It's nu of all those arguments. And it's linear in each one of those arguments. That's why it's called multilinear. Now, some of those covariant tensors of rank 0R are going to be antisymmetric and others are not. In general, they don't have to have any particular symmetry. For the purpose of integration, we will be using covariant tensors of rank 0R for r-dimensional integration later on, which are completely antisymmetric. So consider now an arbitrary covariant tensor of rank 0R, and it may not have any symmetries, but we can project out its antisymmetric part. Let's call that antisymmetric part nu tilde. If nu is the original tensor, then nu tilde is the antisymmetric part of it. We obtain it by applying the so-called anti-symmetrization operator, or the anti-symmetrization map, A. And how does that work? Well, it works in the obvious way. The anti-symmetrized version of nu, when fed R tangent vectors, is obtained by taking the sum over R factorial copies of nu, where each copy has a different permutation of the arguments. So we feed the R tangent vectors in all possible permutations as arguments into nu. Now, every permutation has a unique signature. Every permutation is reached from the identity permutation uniquely by either an even or an odd number of neighboring permutations. And that gives us the signature of the permutation. So we add or subtract those terms depending on whether the permutation of the arguments is an even or an odd permutation. This will ensure that the entire sum here is completely antisymmetric. If you interchange any two arguments, then you get a minus sign, an overall minus sign. We also normalize the whole thing with 1 over R factorial, so that if we do this to a tensor that's already antisymmetric, we haven't really done anything. Why R factorial? Well, how many permutations are there anyway? Well, it's R factorial, because for the first tangent vector, you have R slots to choose from. Put it in there. Then for the next one, you have R minus 1 slots to choose from. Put it in there, and so on. So overall, there are R factorial different ways to putting them in. And so you get R factorial terms. We divide by R factorial in order to not have done anything if the whole thing started out antisymmetric. But if it wasn't antisymmetric to start with, after that antisymmetrization operation, the resulting tensor is antisymmetric. Again, the antisymmetrization may be a bit mysterious. Why would we care about that? Ultimately, we will be able to trace the need for the antisymmetrization back to the antisymmetry of the Jacobi determinant in changes of variables, in changes of coordinate system of multidimensional integrals. That will ultimately be the origin for the need to antisymmetrize those tensors. But it's not clear now. I'm just anticipating that this will come up. So concretely, how do we do this? Well, consider, for example, a covariant 2 tensor. So this is a 0-2 tensor obtained in this way. F is a function, G is a function. We're still working at a point here. Everything happens just at a point of the manifold. Then F is a function germ, G is a function germ about the point P. Then dF is a cotangent vector. dG is a cotangent vector. The tensor product is now an element of the tensor space 0,2, T02, twofold covariant tensor. That thing is not antisymmetric. If we evaluate this 2 tensor, covariant 2 tensor on 2 tangent vectors, this is how we do it. Nu fed 2 tangent vectors, xi1 and xi2, gives us df applied to xi1 times dg applied to xi2. See, the first argument goes in here, second argument goes into the second tensor factor. And by the way, how do we evaluate these things? Remember that when we have the differential of a function to be evaluated on a tangent vector, which is a directional derivative, then this is, by construction, the directional derivative acting on the function, evaluated at the point. That's what we have here. This is xi1, the directional derivative evaluated on the function, times this directional derivative here evaluated on the function g. These are 2 numbers that get multiplied. So that's not symmetric in interchanging xi1. It's not antisymmetric under the interchange of xi1 and xi2. we apply the anti-symmetrization operator, and then we obtain a new tensor of rank 0, 2, one which is antisymmetric, the nu tilde. Nu tilde is A nu, and it is by definition 1/2. This was the combinatorial factor, 1 over r factorial, but we only have 2 here, so it's 2 factorial, which is 2. And then we have df and dg, and we are feeding it the tangent vectors in all possible permutations. And there are only 2, xi1, xi2, xi2, xi1. And this one is an odd permutation, so it acquires a minus sign. So, since this is true for all of the xi, we can also write that the antisymmetrized version of this covariant 2 tensor is this. It's 1/2 df tensor dg minus dg tensor df. Because this way of writing it makes sure that we are feeding the arguments in all permutations. Okay, so this thing, the nu tilde is antisymmetric. Here's a proposition. A, the antisymmetrization operator, is a projector, in the sense that if we apply it twice, it's the same as if we applied it once. Once we've antisymmetrized a tensor, then it stays antisymmetrized. Nothing else happens to it if we apply the antisymmetrization again. Let's check that in the above example. So let's say we apply the antisymmetrization operator twice on df tensor dg. Then we have to apply the antisymmetrization operator on that. This is, we just saw above, the outcome of antisymmetrizing once. Now we have to apply the antisymmetrization operator on this, minus the antisymmetrization operator applied to that. See, it's just linear. The antisymmetrization operator is linear, so we can have it act on that, and then add what it gives when applied to this. Now, A applied to this from above just gives us these 2 terms. A applied to that, again, using what we had above, it gives us this. And if you collect all the terms, you find that you get quarter and a quarter and a quarter. And these 2 are the same. 2 quarters is a half, and these 2 are the same. Again, 2 quarters is a half. So we get this expression, which we recognize is a df tensor dg. So indeed, at least in this example, we proved already, yes, once antisymmetrizing is enough. Now we are ready to define differential forms. So let us look at covariant tensors of rank 0r, where r is larger than 1. You see, if r is 0 or 1, then there's nothing to antisymmetrize. But if r is 2 or 3 or 4 and so on, then the tensor has multiple indices, has multiple tensor factors, and so we can antisymmetrize. So then we define differential R forms, or also exterior R forms, or simply just R forms. We define the space of them, capital lambda R of P, the differential R forms at the point P of the manifold, to be simply all the antisymmetrized 0R tensors. So we obtain the space of R forms by antisymmetrizing all the 0R tensors. The space of R forms is the image under the antisymmetrization operation of the space of 0R tensors. You just go through all 0R tensors, antisymmetrize them, and you get this space. This has a much lower dimension than that space. So obviously, from this definition, if nu is an element of the set of, or the space of differential R forms, then we can conclude it must be antisymmetric, because it's an element of this. It's an antisymmetric 0R tensor. Therefore, if we apply the antisymmetrization operator on this nu, then we get nu tilde, which is the same as what we started from. The antisymmetrization operator does nothing on those which are already antisymmetric. In other words, this is the eigenspace of the anti-symmetrization operator with eigenvalue 1. Now what about r equals 0 and r equal 1? There's nothing to anti-symmetrize. But remember I said that whenever we integrate over r dimensions, then what we are really going to do is integrate in r form. But surely we want to integrate also over one dimension, for example, to one-dimensional integrals. So we need to be able to handle one forms. What could one forms be? It turns out that 0 forms and 1 forms are very easy to define. We had them already. The 0 forms are just the numbers, just the scalars at a point, and over the entire manifold, the 0 forms are just going to be the scalar functions. The differential 1 forms, so these are going to be the differential 0 forms, and the differential 1 forms are simply the cotangent vector space. There's nothing to anti-symmetrize. And that's straightforward. Remember that the anti-symmetrization came from the need to anti-symmetrize in the Jacobian determinant for changes of variables in multidimensional integrals. But if your integral is one-dimensional, the Jacobian is just a number. There's no determinant in there. There is nothing to anti-symmetrize. We don't have to anti-symmetrize. The space of differential 1 forms is directly just the cotangent space. Okay, so the space of differential 1 forms is just the cotangent space. I could also write this as TPM star, or a 1 down there, same thing. Okay, so we have differential forms. Differential R forms. It will turn out to be very useful to turn this vector space of differential R forms, or these vector spaces of differential R forms, into algebras, to give them a multiplication as well. And the reason is that once we have an algebra, we can consider the derivations of that algebra, the linear maps that obey the Leibniz rule. And then again, we get various versions of differentiation. It's going to be just like we did before with the algebra functions on the manifold, or the function germs. There we considered linear maps, linear maps which obey the Leibniz rule, and we obtain the tangent vectors in an abstract way. So here, let's see what we get when we turn the algebra of differential forms, when we turn the vector space of differential forms into an algebra, and then consider derivations on that algebra, linear maps that obey the Leibniz rule. See, in this way, we don't need to bother with limits epsilon going to 0, or in fact, we don't need to bother with any coordinate systems. In order to use a Newton-Leibniz kind of formula to define a derivative, you first have to choose a coordinate system. We'd like to be able to define the key concepts of differential geometry without having to refer to coordinate systems. So we need a multiplication on differential R forms. And that multiplication is the so-called wedge product. Let's say omega is a differential S form, and nu is an R form. I mean, you see, I'm using differential form and form synonymously. So let's say omega is an S form, nu is an R form, and let's say none of the two is just a function, so R and S are not 0. It's just too simple if one of them is a function. I'll cover that as a special case in a moment. So let's say we have an S form and we have an R form. Then the wedge product between the two gives us a differential form of degree R plus S. So we multiply an R form with an S form, and we get an R plus S form at the point P. In the following way. We take the pair, omega and nu, and we map them into the wedge product of the two, and this is supposed to be a differential form again. Not just a tensor, but it has to be a differential form, which means it also has to be antisymmetric. Now, if you took just one differential form and tensored it with another differential form, and you would get another tensor, but it wouldn't be antisymmetric. So in order to have a map from differential forms into differential forms, we have to make sure that this product gives us something that's totally antisymmetric again. And the definition is simply this. You take the tensor product between omega and nu, viewed as tensors, and then that tensor gets antisymmetrized. Put some combinatorial factors in front that will be convenient later on. They could be absorbed elsewhere too, but it's convenient to put those combinatorial factors right here. Okay, so a differential form is just a tensor. It's a covariant tensor, but it's a special kind of. It's an antisymmetric tensor. We multiply two of those differential forms by viewing them as tensors, writing down the tensor product of the two. This gives us a higher rank tensor. And then antisymmetrizing it. That's the outcome of the wedge product. In the case where one of the two differential forms is actually a zero form, and therefore a function, the situation is a little different, because remember that differential forms normally take tangent vectors as input. A differential R form takes R tangent vectors as input and outputs a number, because it's a covariant 0R tensor, right? But how many tangent vectors as input does a zero form take? Well, none. And so you can't antisymmetrize over it either. So the definition that one adopts is this. If C is an element of lambda 0, and at the point that's just a number, on the entire manifold it's a scalar function, and S is an S form, if you have a zero form C and an S form omega, then their wedge product is simply their product. Just multiply. There is nothing to be antisymmetrized because C doesn't take a tangent vector as input. Okay, so whenever we have a function times a differential form, we can also view it totally equivalently as a zero form wedge the differential form. Functions and zero forms are the same, and the multiplication with a function is the wedge product with a function. Same thing. So just remember that when you have a function wedge a differential form, it's the same as just a function times the differential form, just literally multiplication by a number. So the usual multiplication. Now, for example, let's calculate the wedge product between dxi and dxj. That's a cotangent vector. That's a cotangent vector. The wedge product between the two is supposed to be a two form, a differential two form. So it's supposed to be a tensor in the tensor product space of two tangent vectors and totally antisymmetric. Well, here we have it, the formula. So omega is dxi, nu is dxj. Then the prefactor is what? Let's see. This is a one form, that's a one form. So S is 1 and R is 1. So we have 1 plus 1. That's a 2 factorial, that's a 2, and down here we have a 1. So we have overall here a factor of 2. And we have to antisymmetrize the tensor product of dxi and dxj. So when we antisymmetrize dxi and dxj, we obtain this minus that. But remember that the antisymmetrization operator has a combinatorial prefactor of 1 over r factorial, which in this case is 1/2. Multiplied with this 2 gives us just a 1. So this is the wedge product between dxi and dxj. It's this covariant 2 tensor, antisymmetric as it should be. So what are the properties of this wedge product? Well, it has lots of nice properties. It is bilinear. So if these are two differential forms, and then you take the wedge product with eta, then it's distributive. So you can have, this is omega wedge eta plus nu wedge eta, distributive, very nice. Also, if A is a zero form, it's just a function or a number, if it's at a point, then applying it to the first differential form and then wedging with nu, or omega wedged with applied the number here is the same as wedging omega and nu and then afterwards multiplying with a. And very importantly, we have that if omega, nu, and eta are three differential forms of arbitrary degree, then it doesn't matter in which sequence you multiply them together. If you first multiply those two and then wedge with the nu, or first multiply those two and then wedge with the omega, then that's the same. This is associativity. Doesn't mean commutativity. It's just associativity. Commutativity is not guaranteed. It just doesn't hold. Although it holds often, not always. It's graded commutative. It's neither commutative nor anti-commutative. What it is depends on the degree of the differential forms. Omega is an R form, nu is an S form, then one can show that if you swap their sequence and then wedge them, you get the same thing, except for possibly a minus sign. Minus 1 to the power of R times S, which means that if either one of them is an even form, then it's just a plus 1. But otherwise, it can be minus 1. So in particular, if this is a one form and that is a one form, then what? Commutative, anti-commutative? Anti-commutative, right? Because if this is a one form and that is a one form, then R and S are 1, so it's minus 1 to the power 1, which is minus 1. So if this is a one form, that's a one form, then it's anti-commutative. So dx1 wedge dx2 is minus dx2 dx1. The wedge product is very convenient also to build up the space of all differential P forms. Let's say we have a basis of the space of one forms, which is to say we have a basis in the tangent space at the point P. So let's say those theta I running from I equal 1 to n is a basis of the cotangent space. If we are lazy, we might choose those that come with the given choice of coordinate system, but we can really choose any basis we want. So let's say the theta I are a basis in the cotangent space. Well, then when we consider wedge products of such basis vectors, then we get elements of a higher degree differential form space. See, if we multiply R of them together with the wedge product, then we get automatically a totally antisymmetric tensor of rank R, of rank 0R. So therefore, it's an R form that we get in this way. Now, when we take two of those theta to be the same, then we might as well not bother because the whole thing will collapse and be 0. It will not be 0. It will not be independent of what you get when you do it in the other sequence. What I'm aiming at is that by writing down all possible combinations like that, we are spanning all differential R forms. And I leave it to you as an exercise to prove that you get all differential R forms in this way. But as a hint, let me just remind you that when you take two of them and you interchange them, then you pick up just a minus sign, and that differential form is minus 1 times the previous one, so it's linearly dependent. So it's not a separate basis vector. Therefore, and I'm feeling I'm giving already the proof away, but basically it suffices for this reason to have them ordered. You can choose those wedge products of these basis vectors in such a way that the I1 is smaller than I2, is smaller than I3, smaller than IR. Because if they're not ordered, then you can always change the order so that they become ordered, and you're not generating a new basis vector because it's going to be linearly dependent because of the antisymmetry. So the set of all wedge products where the I1 is smaller than the I2 is smaller than the I3, etc., the set of all those wedge products is going to form a basis in the space of differential R forms. For R larger 1. For R equal 1, it's trivial because we are just dealing with the cotangent space, and these guys themselves, by assumption, form a basis. And for R equals 0, well, at the point, it's just a number. We don't need a basis there, we have it already. One can ask, how many of these are there? What is the dimension of the space of differential R forms at a point? Just a moment, Guillaume. What is the dimension of the space of R forms at a point? Well, on the basis of the fact that they are ordered by size of their index there, we can deduce that there are, and choose R of them, which is this number here, n factorial over R factorial times n minus R factorial. And that in particular tells us also that the dimension of the space of R forms drops to 0 as soon as R exceeds n, the dimension of the manifold, the dimension of the tangent space, the number of basis vectors that we have here. And that is plausible because if you have an n-dimensional space, n-dimensional manifold, n basis vectors for the cotangent space, and you write down the wedge product of more than n basis vectors, then some of them have to be the same. Because there are only n to choose from. If you write down more than n, some of them have to be the same. But then by anti-symmetry, that is actually vanishing. You see, theta 1 wedge theta 1 is 0 because it is minus theta 1, right? Remember? We had this. dxi wedge dxj is this antisymmetric combination, and that's the same is true if this is an arbitrary basis vector. That's another arbitrary basis vector. So then if you choose here dxi, or theta 1 wedge theta 1, then you get something minus the same is 0, right? So what we see here is that on an n-dimensional manifold, differential R forms only go up to R equal n, and then there are none beyond that. Which also makes sense if you think about the fact that this will be needed for integration. How could you do a higher than n-dimensional integral in a manifold that's only n-dimensional? Yeah.
Yeah, I thought we defined the wedge product as like a binary operation, and here you just write a bunch of them in sequence. What does that mean? Do you associate?
Yes. Good point. Good point. Remember, it's really defined this way. If you have A wedge B wedge C, then really what this means is that first you take, let's say, here we have the three of them, right? If you want to calculate what differential form you get when you wedge three of them together, you have to wedge two of them because it's a binary operation, as you said. You wedge two of them together and you get a differential form. And then you wedge that differential form with this one. And hopefully this doesn't depend on how we bracket it. If we bracket this way, if we first wedge those two together, and then this one, who's to say that you get the same answer? Well, you are to say, because you can prove it, right? It follows from the axioms that this is associative, so we don't need to write the brackets. You see, so you saw it without brackets, and you were wondering, how come no brackets? It's a binary operation. The reason is you can bracket, you have to bracket, but it doesn't matter which way you bracket, because it's associative, and therefore we can leave out the brackets. And it looks like a more than binary operation, but it's really only binary, except that the bracketing doesn't matter. So let's make this a little more concrete. Let's say P is an element of the manifold, and let's say the manifold is simply R3. But then what are the zero forms? I didn't even write it up. The zero forms are just the real numbers at a point, right? On the manifold, it would be the scalar functions. So the zero forms are just the real numbers. I should write here lambda 0 equal r. What is the space of one forms? Well, the space of one forms is the space of cotangent vectors. It's a cotangent space. And the cotangent space is the span of some choice of basis vectors. Let's say we choose those basis vectors. So we can write the space of one forms as the span of such three basis vectors. In the case of R3, what though is the space of two forms in R3? Now remember, the space of two forms is spanned by all possible wedge products of cotangent vectors which are ordered by the magnitude of their index. And that's what we have here. Space of two forms is spanned by, of course, two forms. This is a two form, that's a two form, that's a two form. And these are the only three two forms which have the indices ordered. You see, this is dx1 wedge dx2. 1 is smaller than 2, fine, matches the condition. Then this one is dx1 wedge dx3. Again, ordered because 1 is smaller than 3. And then here we have dx2 wedge dx3. Again, ordered because 2 is smaller than 3. There are only those three combinations. The space of two forms in R3 is therefore 1, 2, 3-dimensional. How about the space of three forms? Space of three forms is spanned by all threefold products of basis vectors which are ordered. That's the only way you can write down something ordered here. dx1 wedge dx2 dx3. This is smaller than that, this is smaller than that. There's only one possibility. The space of three forms is one-dimensional. One other way of putting it, the space of totally antisymmetric covariant 0-3 tensors is one-dimensional. So you see a pattern here. We start out with one dimension for lambda 1, then it goes up to 3 dimensions, then 3 dimensions, and then 1 dimension again. This is a general pattern. If you have an n-dimensional manifold, then at a point you have lambda 0, which is always just r. Then lambda 1 is always the cotangent space, its dimension is n. And then you go up in the dimension. You go up in the dimension, and then somewhere in the middle it goes down and down and down again. And then eventually the n forms, well, there's only one n form at the point of an n-dimensional manifold. And there are no 4 forms, because there's no way that you could write down a wedge product of dx1, dx2, or dx3, which contains 4 of them, without containing one of them double. And so, therefore, setting everything to 0 because of the antisymmetry. Now, here's a crucial definition. We define now the algebra of all of those differential R forms. It's simply the linear combination of the spaces of differential I forms. As a vector space, it's just a linear combination of them. So we allow ourselves now to write down linear combinations of 1 forms and 2 forms and 3 forms and so on, which is not something we would normally do with ordinary tensors. You wouldn't normally add a cotangent vector plus a tensor of rank 0, 3. They would be totally different animals. But we define here, for differential forms, arbitrary linear combinations of forms of arbitrary rank. Okay? So we consider the linear combination of all those differential forms for all R. That's a vector space so far at every point. But through this wedge product multiplication, and because the multiplication is distributive and associative, it becomes an algebra. It becomes an associative algebra. This is an associative algebra, not commutative, but nevertheless an algebra. It is called the exterior algebra, or also the Grassmann algebra. It's called the Grassmann algebra over the tangent space of the manifold at the point P. By the way, we are not going to do this for a long time in this course, but eventually we will also consider a different multiplication on there instead of the wedge product. And in this way, we can get a different algebra, which is related but not the same. It's called the Clifford algebra. But we're not going to do this right now. We will need the Clifford algebra later for spinors, but for now, don't need that. Okay, so the differential forms, the antisymmetric covariant tensors, form an algebra, the Grassmann algebra, at the point. Now we generalize that globally to fields. So a differential form field is a mapping that associates to every point in the manifold one of those elements of the Grassmann algebra. So it's just like a vector field. But instead of giving you a vector, it gives you an element of the Grassmann algebra for every point of the manifold. Usually one uses for these also simply the terminology differential form, even though it's really a differential form valued function. And we denote it by omega. So we don't really distinguish in terminology or notation between local and global very much, only if it really matters. So these fields then, these form valued fields, form the Grassmann algebra of differential forms. Of course, once we're dealing with fields, the dimensions are infinite, all of them, right? Only at a point will the space of differential R forms be finite dimensional. But if you look at the fields, they will form an infinite dimensional Hilbert space. Now, why did we do this business with the wedge product? We did it so that we obtained an algebra, the Grassmann algebra. And we wanted the algebra because then we can consider derivations of that algebra, and hopefully those derivations give us natural notions of differentiation. Remember what a derivation is? It's a linear map that obeys the Leibniz rule. Just like we defined derivations on the algebra of functions and obtained tangent vector fields, now we have the algebra of differential forms, and we consider derivations on those. It turns out that in this way, we will obtain the so-called exterior derivative and the so-called inner derivative. And you may wonder, what? How can you get two? Before, when we studied the algebraic definition of tangent vectors, we said, okay, linear maps from functions into real numbers, or linear maps from functions into functions if you do it globally, that obey the Leibniz rule, that's tangent vectors, or tangent vector fields. But uniquely so. Now I'm saying, with this trick here of defining the algebra and then looking at its derivations, we get two kinds of derivatives. And yes, that's true. And the reason is that there are different kinds of derivations with subtle differences. And several of those definitions, several of those cases will be important. For example, the exterior and the inner derivations, and there are more. You may wonder, oh, do we really have to do all those things? You've already done them. You've seen them, just not in that shape, not on that level of generality. So here's a definition. A linear map phi from differential forms into differential forms will be called a derivation of degree k, and you see there can be different derivations because they can have different degrees, will be called a derivation of degree k if they map differential S forms, if the linear map phi maps differential S forms into a differential S plus k form. So for example, if you had a derivation that maps S forms into S forms, it would be called a derivation of degree 0. But it could also map S forms into S minus 1 forms, in which case it would be a derivation of degree minus 1. Everything possible here. So a linear map is called a derivation of degree k if it maps S forms into S plus k forms for all S, and if it obeys a Leibniz rule. So when applied to the wedge product of two differential forms, alpha wedge beta, then you obtain what you get when you apply the derivation on the first factor, leaving the second the same, plus leaving the first the same and applying the derivation on the second factor, as it should be for a product rule, for a Leibniz rule. And that's got to be true for all differential forms. So you might think, okay, now we know why there can be different derivations. They can differ by their degree. Well, they can differ by something else too. Namely, there is a notion of Leibniz rule that's a little more general than this. A linear map phi of differential forms into differential forms is called an anti-derivation of degree k if, when we take two differential forms, they are mapped, if let's say it maps S forms into S plus K forms, that's the usual definition as before. The K determines what degree the anti-derivation is. But now the Leibniz rule is a slightly different one. The Leibniz rule is now taking the product of the differential forms, mapping it into phi of alpha wedge beta plus, and then alpha wedge phi of beta. That would be the usual Leibniz rule, but there is possibly a minus sign. Possibly a minus sign. It depends on Q, which is the degree of alpha, the first factor here. If that's a Q form, then we get minus 1 to the power Q here. So for example, if this is a 1 form, then yes, there's a minus sign because it's minus 1 to the power Q. If Q is a 2 form, if alpha is a 2 form, then that wouldn't be so. Now, because of the anti-symmetry, symmetry rules of the wedge product, this is not actually preferentially treating the first factor. So there's possibly a minus sign in there. And it turns out that this complication is very useful. It will come up. This is, so the key thing is, this K determines the degree of the derivation, and whether it's an anti-derivation or not depends on whether or not this thing here is present or not. Extremely handy is this proposition. This proposition says that because of the Leibniz rule and linearity, any anti-derivation or derivation that maps differential forms into differential forms is completely determined on all differential forms if only we know how it acts on zero forms and if we also know how it acts on at least a basis of one form. So in order to specify any derivation or anti-derivation completely, all we need to know is how it acts on zero forms, how it acts on a basis of one forms. And you can think about this. I leave it to you as an exercise to prove that. It's quite straightforward to prove. See, if you have an R form and you want to know how phi is acting on an R form, well, you can write the R form as a sum of products of lower degree forms until you have it down to 1 and 0 forms. And we know how it acts on those. And you can compose that using the Leibniz rule. The Leibniz rule tells you how the derivation is going to act on products of forms. But every differential form is eventually the product of 0 and 1 forms. So with the Leibniz rule, you can work out what the action is. So key thing, we will use that several times. We will use several times the fact that we can completely specify a derivation by only specifying how it acts on 0 forms and on 1 forms. And here is the first example right away, the so-called exterior derivative. It's this D again that you've seen before. So the exterior derivative is going to map differential forms into differential forms. It's going to be an anti-derivation, so it has this minus sign in the Leibniz rule. And it's going to be of degree k equal 1, which means that it will map an S form into an S plus form for every S. It will map in particular 0 forms into 1 forms, 1 forms into 2 forms, 2 forms into 3 forms. but again, it maps also zero forms into one form. In other words, it maps functions into cotangent vector fields. This is what the D did that we had before, right? You take a function and then apply the D to it, you get a differential form. You get the cotangent vector. So it's really, this is what really the D is that we had earlier. Now, in order to specify the exterior derivative completely, in order to specify how it acts on all differential forms, all we need to specify is how it acts on zero forms and how it acts on the basis of one forms. Mm-hmm.
You mentioned the relation of degree of k equals being a negative number. Isn't that would be like inverse of a derivative, and is that how we define integration?
Good question. It's not that. No, it could have been, right? But it's not. It's not going to be that. We will get an antiderivation of degree -1 later on, actually in the next lecture. But it's not going to integrate for us. Okay, so the exterior derivative can be completely specified by specifying how it acts on zero forms, that is on functions. And we already had that, if you think about it, and by specifying how it acts on one forms, on a basis of one forms. And here's the definition. Let's specify how D acts on zero forms. Well, we have to specify how it acts when we feed in any zero form, which is to say any function, and what kind of cotangent vector fit we get. Well, we use the definition we had already. D is mapping functions into their differential. Okay? That is the action of this D operator on zero forms. Now we still have to define how D acts on a basis of the space of one forms. Now, the dxi, we know, form a basis in the cotangent vector space. So they form a basis in the space of one forms, because the space of one forms is the cotangent vector space. So how are we going to let D act on one forms? As simple as possible. We map them all into zero, radically. All going to be destroyed, okay? So dxi maps all the dxi into zero. Now that should be easy. So we now know how the exterior derivative acts on zero forms. Well, it maps the functions into their differentials, and it maps those basis vectors into zero. This doesn't mean that it maps all one forms into zero. This only means that it maps this basis of one forms into zero. It's a slight difference, okay? We will see exactly how that happens. So in a chart, what is it going to be? We had that D is mapping functions into their differential. And a differential, if you remember, is this. It's the sum of the partial derivatives times the dxi. That's a differential of a function. This is how D maps functions into one forms. That is a one form. By the way, let me remind you of what exactly the structure of this is. This, you recognize, is a basis vector in the cotangent space. What is that? That's a function. In other words, it's a zero form. Therefore, this is an ordinary multiplication or a wedge. Your choice. Doesn't matter. Same thing. So we have here zero form wedge one form, if you want. Or we have function times a one form. But it's useful sometimes to think of this as a zero form wedge a one form, where the wedge is equivalently just the multiplication. Because if we now want to apply another D on this, then we can use the Leibniz rule. We have a zero form wedge a one form. We know how that acts by the Leibniz rule. Okay? So, so D maps functions into their differentials, and that's this differential one form field. More generally, we are not so lucky. We don't just have to act with D on functions. No, generally we will have to act with D on that sort of animal here, which is an arbitrary differential S form. We know that every differential S form is a linear combination of these basis vectors, where those guys, these are just basis vectors of the cotangent space, and we know that we can even choose them ordered by size. Okay, so these form a basis in the space of differential S forms, and these are the coefficients in that basis. Again, just as we discussed here, these are basis vectors. Those are just regular functions, coefficient functions. But we can view those coefficient functions equivalently as zero forms. They are zero forms. And this can be viewed as a wedge here, even though it's a trivial wedge, it's just multiplication, because there's nothing to be antisymmetrized. Okay, so the structure is coefficient functions, which is the zero form, wedge this basis in the space of S forms. That is a general differential S form, which we call beta. And we want to find out what D does to it. How does that derivation differentiate the beta? What does it do? D is going to map beta into D beta, but what is it? Well, we can simply use the Leibniz rule. In fact, it's an anti-Leibniz rule, remember? The D is an anti-derivation of degree +1. Okay, so the dB is then given by what we obtain when we apply the D onto that zero form, leaving all the rest the same, plus leaving this zero form the same, and applying the D to the rest. Leibniz rule. Okay, so let's do the two terms one after another. We apply the D, see we have D beta, so we apply the D to this zero form first. Now, the D applied to a zero form is the D applied to a function. Never mind that this thing carries indices. It's really just a function, right? It's just a number at every point of the manifold. So we apply the D to this function here, to this element of lambda 0, in the same way that we did here. This is just like an f here. Namely, we get that. We get a dxi and then the partial derivatives. So let's do this. We apply the D to that. That gives us this. We differentiate the beta, this zero form, with respect to xj. These are all those partial derivatives. And then we get the dxj. You see, we differentiate and then contract with the dxi indices here. And then all the other dxi1 to dxis are over here. Okay? So that's the first term of the Leibniz rule. We've differentiated this part, leaving that part the same. And then we have to add to this what we get when we leave that the same and apply the D to this. So we get plus in terms of the form, well, something or other in front. I mean, not something or other, it's just the beta of x in front. And then the D of this. So D of this. But the D of this is vanishing. Okay? Because, if you remember, of that definition, the D is applied to D, the dxi is sending them all to 0. So, actually, when we apply the D onto the general S form, we are only left with this first term. The second term goes away. It's 0 because by the Leibniz rule, we get D acting on this, plus D acting on that, plus D acting on that, but all of those terms are 0. Okay. Now, so on one hand, we've evaluated now what the D beta is. It's this. Okay, so it's easy to remember. You just have to take all the partial derivatives of the coefficient function and then write down the dxj for the d by dxj here and wedge it with the remainder and you're done. That's how you differentiate, how you calculate the exterior derivative of an S form. And the remaining terms are vanishing. Now, an important proposition here is that the exterior derivative, because of this, the exterior derivative, when acting on any arbitrary differential form, gives us the differential form, which when you apply d again to it, is 0. If you apply the d twice, you always get 0. So the proposition is that if you now apply the d again onto this, you get 0. The claim is that d applied to that is 0, no matter what beta is. This is a very important equation that whose importance goes way beyond differential geometry. First, let's prove it, and then I'll tell you a little bit about it. So we apply d again on the outcome of our calculation. So the outcome of our calculation was that d beta is this. And now we apply d again. Remember what we have to do? When we apply d to this differential form, we have to calculate the partial derivatives of the coefficient function with respect to the xj, and then put a dx here again with the wedges. That's all we have to do. Here's the outcome. d beta is given by now the second partial derivative, because one partial derivative we already had. Now we differentiate again with respect to all the variables. Then the dxk gets a dxk here as well. All those wedges. And that's 0. Why? It's 0 because these guys are antisymmetric. You remember the wedge is antisymmetric for basis vectors of the tangent space. So in particular, this business here is antisymmetric in k and j. If you write the j here and the k over there, I mean, if this is 1 and this is 2, then this is the same thing as if it was 2 and 1 up to a minus sign. But partial derivatives are symmetric. If you first differentiate with respect to xj and then xk or the other way around, same thing. So you have a symmetric matrix multiplying an antisymmetric matrix that is always vanishing. So indeed, for purely algebraic reasons, this has nothing to do with geometry. It's really just algebra. Antisymmetric contracted with symmetric is giving you 0. For those reasons, we have that d squared is equal to 0. And that is amazing. I can't tell you the full picture in detail yet. We will get to that later on in the course. But this equation justifies the name, another name for what d is. D is also called the co-boundary operator. Why co-boundary? Why co and why boundary? Now, what is the boundary operator? Now, a boundary operator is what its name says. You take a manifold, and the boundary operator maps it onto its boundary. The boundary is itself a manifold. Think of a manifold like a flying carpet. The boundary operator will map it into its boundary, which is like a one-dimensional line, right? Now, what happens when you apply the boundary operator twice? So you take your flying carpet, the boundary operator maps it into the boundary of the flying carpet. Now you have this circular thing in space, right? The boundary of the flying carpet. What's the boundary of that? 0. There is no boundary, right? Because it's a closed thing. It has no beginning, no end. Now, in the case of the flying carpet, it's quite obvious, but it's always true that boundaries don't have boundaries. If you apply the boundary operator twice, it's 0, it's empty. So there's a boundary operator which, when applied twice, gives you 0. This is a co-boundary operator, when applied twice, gives you 0. And the amazing thing is that this operator, as we will later see, is actually the dual of what is geometrically the boundary operator. So this is actually the same statement as the statement that the boundary of a boundary is empty. And the amazing thing is that this is true for purely algebraic reasons. The fact that the boundary of a boundary vanishes is true for purely geometric reasons. And the connection we will find out later on, but we will need to relearn how to integrate using differential forms for that purpose. And then we will see why it's justified to call D the co-boundary operator. Some more examples just to show you that what you might think of as being exotic now is not really exotic. You've seen all of that before, at least in special cases. So for example, let's say the manifold is R3. And the functions, and here we have functions on the manifold. Then the differential of the exterior derivative applied to those functions just gives you this, partial derivatives, and then the dxi as we discussed before. So that's a one form here. And this is a vector in the three-dimensional cotangent space. Its coefficients are those three numbers here, d by dx1, d by dx2, d by dx3 of f. Remember, you've seen that before. You've known this as the gradient. If f is a, let's say, electromagnetic potential, phi, then these three numbers are the gradient field, the electric field corresponding to the electromagnetic potential phi. So what we see here is that if phi is an electromagnetic potential, then d phi is the electric field. So the electric field is naturally a one form. The electromagnetic potential is naturally a zero form. And d relates the two. D is just d when acting on functions gives you the gradient. So now you see that the coboundary operator, the exterior derivative, is just the gradient when acting on zero forms. Let's see if we can find out what it does on one forms, also in familiar terms. So now let's say we are dealing with a one form, cotangent vector field. So here we have a generic cotangent vector field. This doesn't have to be, the gamma I don't have to be the partial derivatives of a potential anymore. It's just any coefficient functions. Okay, so an arbitrary cotangent vector field can always be written in this way. Then what does the d do to it? We are still working in R3 here, right? So the manifold is R3. So what then does d, the exterior derivative, do to it? Let us define beta as the result of applying d on gamma. Well, how do we get it? Remember, we view this as a zero form. This is a one form. There's a wedge product in between them. We can apply the Leibniz rule. What we get is that we have to take the partial derivative of this. We get a dxi and the wedges over here. By the Leibniz rule, we also have to apply d to that, but that's vanishing, so that's all we have to do. So we get this. This is the outcome of applying the exterior derivative on gamma. Now, we can, here we're summing over all I and j, but we might as well just sum over all I smaller than j, because remember that these span a basis of the space of two forms, even when we order them, even when the j is always smaller than the I. So let's do this. Let's just sum over all I smaller than j. Then we have these terms as well with a minus sign. You see, if we order them ji and ij, then they differ by a minus sign, so we get these terms here. And let's explicitly write out what the basis vectors are. The basis vectors in the space of two forms are dx1, dx2. You see, 1 is smaller than 2, dx1, dx3. Again, ordered dx2, dx3. And these are the coefficient functions in front of those three basis vectors. And there are three of them. In R3, it is convenient, therefore, to bunch them together in a triplet and write it as if they were vectors, as if the beta 1, beta 2, beta 3 were components of a three-component vector. They are not, of course. But you see, they're coefficients of a two form. They're coefficient functions of a two form. But it's convenient to write them as a three-component vector. And those of you who come from the physics side, I know that some of you come from math, but those of you who come from the physics side will recognize what these things are. These are the components of the curl of gamma. So what you see here is the kind of thing that you get in electromagnetism as well. So what you see here is that when you apply in R3, when you apply the exterior derivative on a one form, then you get a two-form whose coefficient functions are the curl of the cotangent vector field that you started with. Physicists like to call this triplet a pseudo-vector field. And that's because physicists know, of course, that it's not a vector field. It doesn't transform properly. There is some weirdness in the way that it transforms under change of charge, and that is because it's not really a vector field. The curl of a vector field is not a vector field. The curl of a vector field is really, of a covariant vector field, is really a two-form, and it transforms a little differently from a vector field. Now we can also see deeper connections here. If you remember from electromagnetism, or from an earlier course in differential geometry, when you have a gradient vector field is always curl-free. So if f is a scalar function, nabla f is the gradient of it, and then you take the curl of that, well, that's vanishing, always, no matter what this scalar function is. This is a special case of this co-boundary property of the exterior derivative. Because remember what it means that this is a gradient vector field. You see, if beta is the d of gamma, then the curl of beta is the d squared of gamma, and that's 0 because d squared is always 0. So the fact that gradient vector fields are curl-free is a special case of d squared acting on any differential form is vanishing. Now this leads us to a definition. You see, apparently it is special. It is something special when a differential form, when you apply d to it, it vanishes. We say that a differential form is called closed if the coboundary operator acting on it is annihilating it. We saw, for example, that any beta that's the d of gamma, of some gamma, is closed. Right? Any beta which is the d of some differential form gamma is closed because if you apply the d to it, it's vanishing because you have the d squared now. But this leads to a question that turns out to be surprisingly deep. The question is, are all closed differential forms of that origin? So if omega obeys that equation, does it mean that omega must be the d of another differential form so that the d squared equals 0 is achieving this? Or could it be that there are omegas which are not the d of some other differential form, and yet the d omega of it is vanishing? It turns out that this question is a very deep one, and it suggests another definition to have the proper language to study that. A differential form omega is called exact if it is the d of some other differential form. Now clearly, if a differential form is exact, so if it is the d of some other differential form, then it must be closed, because the application of another d will certainly produce 0, because we now have the d squared. So clearly, every exact differential form must be closed, because d squared is equal to 0. The key question is, if a form is closed, does it mean that it's also exact? If d omega is equal to 0, does that mean that omega is the d of something? And omega being the d of something, you see, omega being the d of something is as if nu were the antiderivative of omega, right? Because this is like a differentiation. Just keep that picture in mind. So how are closedness and exactness related? It turns out that that is a global question, a question that cannot be decided locally on the manifold, but only globally. It depends on the global topology of the manifold. And by topology, I mean now the other meaning of topology. I don't mean the topology in the sense of epsilon neighborhoods and so on, open neighborhoods. I mean topology in the sense of the manifold possibly having holes and handles and so on. It depends on how many holes and handles a manifold has and whatever the higher dimensional generalizations of holes and handles are. Here's the simplest case. Assume that a manifold is contractible. Contractible means it means that there is a function f from the Cartesian product of 0, 1 and the manifold into the manifold such that, well, you can view this as a time variable running from 0 to 1, such that at time 0 we are dealing with a map that just maps every point of the manifold into itself, and at time equal 1 it maps every point of the manifold into just one particular point of the manifold, and f is supposed to be continuous. An intuitive picture is simply this. This manifold is contractible. It's just in one piece. And you can see it in this way. If you choose a point here, x0, then you can map the manifold in a continuous fashion into a smaller manifold until everything is sucked up by that point. You can do that in a continuous fashion. It's like water draining and the water always hanging together in a continuous fashion. There's nowhere anything discontinuous happening. You can contract the manifold to a point without obstacle in a continuous way. This manifold has a hole. It is not contractible. And you can see it this way. If this were a patch of water and you want to suck it all into that point here, well, at some point, this patch of water has to rip apart here. Right? It has to rip apart in order to clear up the space down here. And that ripping cannot be done continuously. So that's a contractible manifold, and that's not a contractible manifold. And it turns out that for contractible manifolds, exact is the same as closed. That's the Poincaré lemma. It says that on a contractible manifold, if a differential form is exact, then and only then it is also closed. To remind you, gamma exact means it's the d of something. And gamma closed means that the d of it is 0. Okay, so it goes both ways. This direction is always true, contractible or not, because if it's the d of something, then applying d again always gives you 0. That is the non-trivial direction. Okay, but if it's not contractible, so if it has a global obstacle to this shrinking, then it's not the case. The Poincaré lemma then doesn't hold. So for example, Rn is contractible, but Rn with a point taken out of it is not. Because the patch can be as small as you want, even one point will do it. So in general, we only have that gamma exact implies gamma is closed, which is because d squared is 0. So what you see is that we obtain here a tool for classifying global topology. Very important, because if somebody gives you a 27-dimensional manifold and another 27-dimensional manifold, and you are supposed to compare them, or you're just supposed to find out whether one of them has holes or not, but you're given those manifolds in an implicit way as solutions to some equations or whatnot, how do you go about it? How do you find out, for example, whether it's contractible or not? Or more complicated questions about it. Very difficult because we don't have the visualization for it. However, whether or not a differentiable form has d of it is equal to 0, or whether or not it is the d of another differential form, that doesn't need any intuition. You don't need any geometric imagination for that. It's just algebra. You just check, is there or is there not a differential form of which it is the exterior derivative? Is its exterior derivative 0? That's something that you can do algebraically. So you can check for contractibility, for example, by purely algebraic means. So you see how there's a connection between abstract differential geometry and algebra on the other side. The theory that stems from that observation is called the Rham cohomology theory. Now at this point, when we need 5 more minutes, I'd like to take you on a rocket ship trip up to the mathematical stratosphere, where we'll have a bit of an overview of the mathematical landscape so that you see where all of this fits in. I think it's beautiful. It's not necessarily part of the stream of our course, but I think it's very interesting. So this is not the only cohomology theory. A cohomology theory is a theory that tries to get a handle on the global structure of manifolds, preferably in an algebraic way. There are other cohomology theories too. And that's good because none of those cohomology theories is actually complete. None of them tells us everything about the connectivity properties of a differentiable manifold. So for example, there's K-theory. Now, this is a cohomology theory which uses a different observation. There's only one way to put a vector bundle on a contractible manifold, but there are generally many ways of putting vector bundles on non-contractible manifolds. So it's quite similar to this closed versus exact. For contractible manifolds, one algebraic thing is true, and for non-contractible, another thing is true. Here it's about the possibility of putting non-isomorphic vector bundles on a manifold. If you remember that example here, we can have that there is a twist. If this is a manifold and then we put two vector bundles, we put a vector bundle in there, and here's a local trivialization, there's a local trivialization, and the isomorphisms may have a twist in them, just like a Möbius strip would have. But I don't want to say much more about K-theory and these things. I'd like to give you an overview of what cohomology theories are and what part of general structure cohomologies, what cohomology theories are part of, more generally. So now we really take off. Okay, so cohomology theories are always natural transformations. And natural is really a technical term here. So there are natural transformations between two so-called categories. Now you may wonder, what are these things? What's a category? What are natural transformations? Now, here's a definition of a category. It's not going to be entirely accurate. I'll tell you in a moment why. So a category is a set of objects and morphisms. So here you have your set. It has objects. These are those dots. And the morphisms are arrows between them. I'm not entirely accurate here because not technically a set, it's a class, and there's a difference between sets and classes and so on. But for our purposes, it suffices this level of accuracy. So a category is a set of objects and morphisms. So it's a bunch of things. Here are the objects. And there are morphisms which are arrows in between them. And we also want arrows that, the possibility of arrows that emanate from an object and go back to the same object. And in general, there will be many, many more arrows than I drew here. I just grew tired of writing too many arrows. It wouldn't look very nice. So what axioms does the category have to obey? Well, basically, here are the axioms. If there's an arrow from an object A to an object B, and an arrow from the object B to the object C, then there must be also an arrow directly from A to C. This is one of the key axioms. We also want associativity. If you have an arrow from A to B, from B to C, from C to D, then, if you combine those two arrows, you get one arrow that gets you right here. And then you combine it with that. You should get the same arrow as if you first combine these and then that one. It should be associative in that sense. And we also want that every point here has an arrow emanating from it that goes back to itself. See, this is a fairly innocent-looking, very simple structure. A bunch of objects, a bunch of arrows in between them. Those arrows should be composable in an associative way. And if there's one from A to B, one from B to C, there's got to be one from A to C. What are examples of that? Here's an example. Category of vector spaces. Every dot is a vector space. How many vector spaces are there? Well, infinitely many, right? So there are plenty of dots in this. All kinds of vector spaces. This category contains all vector spaces. Every point here is a vector space. And what are the arrows in between them? Well, the morphisms, the arrows between the vector spaces, the arrows between the objects, are the linear transformations, right? Are the structure-preserving maps between our vector spaces. And it turns out that by defining the objects to be vector spaces and by defining the morphisms, the arrows, to be linear maps, we obey those axioms, right? If there's a linear map from here to there and from here to there, there's going to be a linear map from here to there as well. And you can compose them associatively as well. And there are always linear automorphisms as well. So let's call this category the category of vector spaces VEC with an underline. Here is another example. The category of associative algebras. You see, we're high up in the stratosphere now, in the mathematical stratosphere, and we see all the associative algebras at once. All of them. Each dot is an associative algebra. Our Grassmann algebra from earlier is one of them. Okay? And there, the algebra of function germs is another one of them, and so on. All kinds of associative algebras. And we define the arrows in between them to be algebra homomorphisms. If we do that, then we can check that the axioms again hold. So we have now a category of associative algebras. Let's call it ALG, for lack of a better name. And the beauty of category theory is that there's also this category. It's the category of categories. Okay? You see how this is high up? So every point here is now a category. Okay? So this might be the category of vector spaces. That would be the category of associative algebras. Here could be the category of Lie algebras. That could be the category of rings, and so on. So the objects are categories.
Can it be a category of categories?
Yeah.
Can I be in the set of categories?
That's why I was not allowed to use the word sets there. It's classes. Exactly. You have to be careful for that very reason. That's right. Okay, so we have the category of categories, and the objects in there are categories. And we saw a few examples of them. And for every algebraic, for every structure in math, everything that obeys some axioms, you can cook up a category. And the morphisms are whatever leaves those structures intact. Okay, so we have the category of categories. The objects are categories. But what are the morphisms? Maps between categories, right? So a morphism in the category of categories is, a morphism is a map from a category to another category. It could be, for example, a map from the category of vector spaces into the category of associative algebras. It would have to be a map that maps the objects into the objects, the morphisms into the morphisms, in a structure-preserving way. Those morphisms, the morphisms in the category of categories, have a special name. Of course, they're just morphisms again, but they have a special name. They're also called functors. Not functions, but functors. And they're also called natural transformations. A cohomology theory is a natural transformation. A cohomology theory is a functor. But between which categories? So a cohomology theory is the following. So here's the category of categories again. Consider one dot here. Let's say this dot is the category of differentiable manifolds. And that is the category of, let's say, abelian groups, commutative groups. It would seem that they have absolutely nothing in common. So here's the category of differentiable manifolds. What would be the object? Differentiable manifolds, right? This differentiable manifold, that differentiable manifold, and so on, right? So this is a category where the objects would be differentiable manifolds and the morphisms, the arrows, are diffeomorphisms. Here we have a category, and that category has as its objects the abelian groups, and the morphisms are the group homomorphisms. And then there may be an arrow between them. There may be several arrows between them from the category of differentiable manifolds to the category of abelian groups. Each one of those arrows is a cohomology theory. So here's the picture. Here's the category, let's call it diff, of the differentiable manifolds. Here I plotted two of its objects. There will be many more objects, of course, but I plotted just two of them. This is one differentiable manifold, that's another differentiable manifold. Here's the category of abelian groups, of commutative groups, full of objects, each object being a commutative group. And between differentiable manifolds, there are arrows, diffeomorphisms. I mean, if there is a diffeomorphism between two manifolds, then it will be an arrow. And when two groups have an algebra homomorphism between them, then we draw an arrow. Now, this is an object in the category of categories. That's an object in the category of categories. And this is a morphism in the category of categories. It maps from this object to that object. That's a natural transformation. It's a cohomology functor. It maps differentiable manifolds into abelian groups. So cohomology theory maps differentiable manifolds into abelian groups and diffeomorphisms into group homomorphisms. And the point about this is the following. If two of those images, two of those groups don't have an algebra homomorphism between them, then we can already tell that the two pre-images, those two differentiable manifolds, cannot have a diffeomorphism in between them. So they are really different. And this is how cohomology theories allow us to distinguish, to categorize differentiable manifolds, namely by categorizing abelian groups. Now, this is always a simplifying picture. This is always a simplifying picture. Not every structure in here is distinguishable over there, but a lot of it is distinguishable. And so, as we will see, the RAM cohomology and K-theory are just different ways of mapping differentiable manifolds into abelian groups in such a way that the map is compatible with the category structure here and the category structure over there. I mean, with the structure of different diffeomorphisms and differentiable manifolds here, and algebra and abelian groups and group homomorphisms over there. You had a question?
I was going to say, do you have an example of a map?
Yes, it's just a little too early. I mean, okay, so the de Rham cohomology will map onto on an abelian group, right? And it will map onto the quotient vector space of the closed differential R forms modulo the exact differential R forms. That is a vector space, and as such, also an abelian group. It's a little early, but we will see that later on. Now, in this course, however, we will not pursue this much. I just wanted to show you that perspective from category high up, because just like mathematics could be built on set theory as the floor, as the ground on which everything is built, mathematics could also be built on logic as the ground, as the first definitions, the place of the first definitions, and everything is built up from there. You can also build all of mathematics from category theory, build everything up from there. It's little known, and it's not used in physics as yet, at least not in any significant amount, but maybe it should be. And the reason why we are not going to use category theory or anything of that really later on in the course is that general relativity is a theory where everything that's important happens locally rather than globally, I mean, as far as we know so far. And therefore, while this is very important to find out global structures of differential manifolds, space-time, as far as we know, is globally relatively trivial. So I just wanted to show it to you, to show you the lay of the land. But for general relativity, it seems so far we don't really need it.
So then just now, you talked about the quotient space of that stuff, right? Now, those obey certain universal properties, correct? So whenever you have a universal property on one side, can you find the exact universal property on another side?
No, this is always forgetful here.
Okay.
Yeah, and you see, you can imagine, because this category is much more complicated than this one. Commutative groups are really a simple thing, and they can be very well classified. But differential manifolds are much more complicated. So the general idea is that you have something very complicated category. Then you invent some forgetful natural transformation into something that's much easier to handle. I mean, for example, let's say the category of knots. Imagine somebody gives you a piece of string which is knotted in a very complicated way, and another piece of string which is also knotted in a very complicated way. And now your job is to find out whether the two knots are actually identical or not. How do you do that? Identical in the sense that if you just turn around, I mean, you hold one of the knots fixed, and the other one you turn around and you pull and tug, but you're not allowed to cut and glue, of course, but you just pull and tug, and then maybe you can, maybe you cannot bring it into the exact same form as the previous one. So by that measure, you have to find out, are they the same knot or not? How do you do that? It's very, very difficult. But what you can do is you can map, you can take the category of those knots and diffeomorphism, and there are maps, pulling and tugging on those strings that gets you from one knot to another knot. That would be the analog of the diffeomorphisms. And so you get a category of those knots, and then you can map that into a much simpler category, such as a category of polynomial functions. And that's in fact what's being done. So now you have two categories. You look at natural functors, and then in this way you can start classifying knots. You map knots onto polynomials. If the polynomials are different, you can tell that the knots are different. If the polynomials are the same, you cannot yet tell that the knots are the same. But at least it's a start. And knot theory works with these things. You can look them up under the name of Kaufman or Jones polynomials and so on. So this is not the only example of category theory at work, but it's the first one. Category theory was invented for this particular purpose, actually, for these two. And then they realized that this is a much more general structure that you can use in many circumstances.
So you can always look up some functor between any two categories. And is it useful to have a concept of the number of functors that you can come up with between two categories?
This is a very difficult task, and nobody knows how many functors there are. Nobody knows whether we can, even in principle, find a complete set of them so that we have a complete categorization there. It's very difficult. Yeah, it's a big deal when you find a useful new functor, because you're inventing a whole new theory of cohomology.
That's why I was asking if the universal properties can convey an existence of such a functor.
No, little is known about that. Right, I think we are done. Here I'm just saying that, in this course we are concerned mostly with the local rather than the global properties, so cohomology is not going to play much of a role. The next thing that we'll do is study the inner derivations. We did the exterior derivative, the d. Next derivative we're going to do is the inner derivation, and then onwards to integration. Okay, that's it for today.